My latest project is to make some realistic stop signs for the level crossing on my model railway, including flashing lights to warn of approaching and passing trains. The challenge being to include all the electronics into something that's going to be convincing at a small scale. But rather than trying to adapt some off-the-shelf signs, I think I can go one better, making something more realistic from scratch. And instead of a commercially available circuit board designed for this purpose, I'm going to go my own way with the electronics as well, using a Raspberry Pi Pico microcontroller programmed for the flashing light sequence. Firstly because at around about £7 or even less, it's cheap, but also because it's scalable, with the potential for adding sensors to detect oncoming trains, sound effects, or even servos to operate the gates. But for this video, I'm going to just stick to the lights, starting by building and programming my controller. I'll be modelling the signs themselves in phase 2, so feel free to skip forward if you want. First of all, let me introduce the Raspberry Pi Pico, which may be unfamiliar to some railway modellers, but is perfect for trackside electronics. It's an inexpensive microcontroller board, a kind of computer light with an array of pins which we can program as inputs or outputs, ideal for controlling a project like ours. And we'll start by pushing those pins into a prototyping breadboard, before wiring up the components. We're going to program it to control our flashing LEDs. Eventually these will be tiny surface mounted ones, but for now I'm using regular ones, 2 red and 1 amber. Each has 2 legs, the long one is the positive, the short the negative, and we're going to push those into our prototyping board, which has a grid of holes interconnected behind the scenes into rows and columns. The long legs are going into 3 spare columns beyond the end of the Pico, and we'll be making further connections from there. All the short ones are going into this row along the edge of the board, and they'll share a common negative connection to one of the ground pins on the Pico using a short jumper cable. Each anode will be connected to its own output pin, which our program will turn on and off. But without a resistor, our Pico's 3.3 volts would blow our LEDs, so I'm adding one for each, bridging the gap in the columns across the centre of the board. At the moment the resistance values are slightly arbitrary. We'll be tweaking those later to get the perfect brightness. So what have we got so far? We've got the cathodes of the LEDs connected to one of the Pico's negative ground pins, and the anodes to their resistors, which now need to connect to the output pins on the Pico, using a short jumper cable for each to complete the 3 circuits. Of course the Pico has lots of pins we can choose from. Most can be used for outputs and inputs, and I've just chosen 3 in a row that are convenient for my wiring. But you will need to visit the Raspberry Pi website and take a look at the pin out diagram, and as well as checking that they're okay, make a note of the numbers. I'm using 21, 20 and 19 on the right hand side, and it's those numbers we'll need for the code, which we'll come to in a moment, but first we've got to set up our Pico. For this we'll need a host computer, complete with screen and keyboard, in my case a Raspberry Pi 3B, but you could use a PC or a Mac. On this we'll be writing the code and then uploading it to the Pico, which can then execute the program when it's unplugged and on its own. But first we must install some firmware, which it will use to run any programs, in this case Micropython. If you've not done this before, I recommend watching my short setup guide, which you can find in the link above. But if you just need a reminder, let me scoot through the process. As with the pin-out diagram, you can find everything you need on the Raspberry Pi documentation website, including the download links for our particular board. The downloaded file being installed by dragging and dropping onto the RPI RP2 that only appears when the boot cell button is held down when plugging in. That vanishes after installation, so to find anything that's on our Pico, we have to go through something like Thonny, and with the Files pane open, we can see a space where we can save our programs, being given the option between our host computer and the Raspberry Pi Pico whenever we save something new. In this case, the yet-to-be-written program for our level crossing lights, the code for which we can get on with now. I'm still very much a coding newbie, so I'm going to keep this simple, and hopefully easy to follow for other newcomers. Mercifully, Micropython, the program we're writing in, is pretty straightforward, and we start by importing some modules from its internal libraries, Pin from the machine library, and Sleep from UTime. You'll get the idea of what these do when they crop up in the code, and the first one we're going to use is Pin. The machine library is for all the hardware kind of things, like the GPIO pins, and we're going to assign pin 21 as an output for the red LED on the left, the one we wired it to on the breadboard. The amber in the centre is going to use pin 20. Just use exactly the same wording and punctuation as above. It's important to know that the capital letters do matter, although the spaces not so much. Also note that the number of the pin is not the same as the number of the physical leg as we saw on the pinout diagram earlier, and it's GP19, not 25, that we're using for our right-hand red. Now we need our LEDs to do something, and we're going to start with an infinite loop, which kicks off our program with a while true statement, and it'll run through all the lines of code until it gets to the end, and then start all over again. My plan is to gradually build up the program, beginning with a very simple iteration, going through the light sequence when the program is run. We'll start by ensuring the two red lights are off, and not left on from a previous run of the program, and at the same time turn our amber light on, giving it a binary value of 1. This is what happens in real life when the gates are about to close, and the orange light will stay on for around about 3 seconds. So we want our program to pause, or sleep, for that amount of time before going on to the next bit, which is when the orange light goes out and the two red lights come on together. So we want to change our value for AC to 0, and for RL and RR both to 1, making sure we get the full stops and the brackets, or more accurately parentheses, in the right places. It only stays like this for a very short amount of time before the lights start alternating. So we want our program to sleep in this state for just 0.75 of a second before moving on to the next line. Now we want the light on the left to stay on while the right one goes out. The left one isn't changing, so I don't really need that line of code, but you'll see in a second why I've put it in. But the right one does need a new value of 0. And we can hold it like that, again for 0.75 seconds, by sleeping the program. Then I want to switch it round. Left light off, right one on. At this stage in the programming, my timings are still a bit approximate. They're based on our local level crossing, which is just down the road, so I'll be able to check them when I'm finished, and tweak as necessary. Now we come to the bit where they flash backwards and forwards, the wigwag, and that's why I put in that extra line for the left-hand LED, so we can copy the entire chunk. And for testing purposes, I'm going to paste that in after the code we've got. Now let's see what happens when we run the program. The orange light comes on for 3 seconds, then both red lights briefly, before flashing left, right, and then back to the beginning with just the orange light, for the whole sequence to start again. Obviously that's not what happens in real life. The lights would continue flashing until the crossing is clear. For this we could paste many multiple copies of our flashing light sequence, one after the other, for the entire duration. Or we could do this, which is to set up another infinite loop inside our first infinite loop. Then when the program gets to here, it will start this bit over and over again, rather than going all the way back to the beginning. And we'll only need one pair of instructions, which will just keep on repeating. Now, after the initial orange light sequence, and our pair of red lights, we get the wigwag, which will just continue until we manually stop the program on our host computer. But that won't always be connected, so what we need now is a way of doing that on the Pico itself, which brings us to the stop-start buttons. Earlier, I used the acronym GPIO to describe the pins. This stands for General Purpose Input Output. We've already seen how output pins work, and now we come to inputs. I'm going to be using these really neat little buttons, or more properly, tactile switches. These have 4 contact pins, the right size to push into our breadboard. But these are actually 2 pairs, and when the button's pressed, the ones on the right make a connection to those on the left. So we can actually get away with using just 2 of them. One will plug in directly next door to one of the pins. The other will connect to the Pico's 3.3 volt output. And by using diagonally opposite ones, we ensure they're not from the same pair. So I can just bend up and snip off the ones we're not going to use with my trusty track cutters. Now my direct connection method is really good for reducing the amount of wires we need, but it does have a downside, as with only half the pins plugged into the breadboard, the buttons are really wobbly, so they do need something else to hold them in place, and a little bit of white tack is a good temporary solution. And with my start button installed, I can get on with prepping the stop one. Now it's worth pointing out here that push buttons are not the only inputs we can use to start and stop our program. And we could replace them with some kind of sensors, which would remotely trigger the lighting sequence as an approaching train passed a certain point ahead of the crossing, and another to stop the sequence when the train is passed. But for the moment, we'll just stick with the manual method. Then to complete the wiring, I just need a common positive, supplying 3.3 volts to each button via a little jumper connected to the outer row of the breadboard. Now before I get to the coding, I just want to summarize our wiring using our pin diagram again. Each button is connected to the 3v3 output from the Pico, which becomes an input into pin 22 when the start button is pressed, and likewise pin 27 for the stop one. And it's those numbers we're going to use in the code, as we did with the outputs for the LEDs. The structure of the code is also very similar. We start by calling our button something, and then assign the number of the pin to it. But instead of a pin out, we want it to be a pin in, which will read a push of the button as a binary 1. But the pin status is a little less certain when the button isn't pressed, so this extra bit of code uses an internal resistor to make absolutely sure it is 0. I have to admit I don't fully understand this, but that doesn't really matter. I just have to know it's going to work. And I can use a copy of the same line for the stop button, just changing the name and the pin number. Now we want to set up the conditions under which the lighting sequence will start. The program's already running the infinite loop, but we can get it to only go on to the next stage if the start button value changes, by adding this line right at the beginning. Then we'll need to indent every single line of the code, so they're all covered by that condition. And when we get to the bit for the repeat, the bit for the wigwag, we need to make sure that we're double indented on all subsequent lines of code up to the end of the program. Now we need to remember that the button push doesn't launch the program, it just moves it on to the next stage, and we've got some preconditions that need to be met first. We want both of our red lights to be off, so I'm just moving those 2 lines up the sequence of events, so they're before the if. We also want the amber light to start out off, only coming on after the button press, so I can copy that too, and change the value to 0, making sure all my indents are correct. Then even though the program's already running, nothing will happen until I press the button. That will initiate the light sequence, starting with the orange and then the red flashing lights, which will carry on until we find a way of stopping them, which brings us to the coding for the black button. We're going to be using an if condition again, but the tricky bit is working out where to put it. Having been through the initial lighting sequence, our program is now in the wigwag loop, and it's here that we want it to check if the button's been pressed. And if it has, it will have a value of 1, and we can use that to halt the program and start again from scratch, using a break instruction. And just to make it super clear what we wanted to do if it hasn't been pressed, we can use else to do a wigwag. Then it's back up to the beginning of that particular loop, where the program will check the black button again, and it will continue looping until the button is pressed. So we now have a fully functioning prototype. The white button starts the sequence, with the orange light on for 3 seconds before the red lights come on and start flashing left, right, until we press the black button, which sends the program back to the beginning with all 3 lights off, ready to start again when the white button's pressed. Finally, from the coding side of things, after a couple of tweaks of the timings, we need to turn it into the program that starts automatically when the Pico's powered up, and for this we need to change its name to main.py, so Micropython knows to run that rather than any of the other programs. Now we need to miniaturize everything, and I'm starting out with a scale prototype, the build of which I'm going to quickly run through, so you can see how I arrived at the final design. The first thing we need to know is how big they should be, and with a bit of googling I found my way to this .gov.uk website, which not only has all the dimensions, but also a scale diagram, which I can drag and drop onto the desktop of my computer. From there I can import it into a page layout program, in my case Adobe InDesign, where I can start making the calculation for my 00 gauge version, dividing the width and the height by 76, which gives me a scale size of almost exactly 18 by 12 millimeters. And I can draw myself a rectangular picture box of exactly that size, just keying in the numbers for the width and the height, before pasting in a copy of my image, which can be scaled proportionally until the sign itself fills the rectangle. I'll be coming back to this later to refine the design, but for the purposes of our prototype, this is good enough, giving us a clear idea of the size we're talking about, and how small our components are going to need to be. First of all, we've got our LEDs, which are considerably smaller than the ones we used for our controller prototype. The lenses are about 2mm across, and the body's roughly 3.5 by 3. They're designed for mounting on the surface of a circuit board, with metal pads rather than pins for the cathode and the anode. The cathode being marked by this little triangular nick, the anode obviously on the other side. And for now I'm going to be soldering them onto a bit of Vero board, with conductive copper strips along the width. It also has holes for more traditional components, but we won't be needing those. So on with the soldering. I've cut myself a piece of board just 3 strips wide, and I've scratched off a little bit of the copper cladding to divide that first one into 2. That's going to be the top of my sign, where my red lights are going to be side by side, and I'm just laying down a bit of solder on the strips for my right-hand LED. That middle strip is going to be the common negative for all 3 LEDs, connecting to the ground on the Pico just like on the prototype. So I'm soldering to that the side with the notch on my first LED. That's the cathode. The anode is then soldered to the half strip, pushing gently down on the LED to get a good contact, and then repeating the process for the left-hand red light, starting with a bit of solder on the strips. You'll notice that the LEDs themselves don't have red lenses. Instead, the colour is created by the wavelength of the light, so it's a good job my eBay supplier clearly labelled the packets. And in case you're wondering, I paid £2.79 for a strip of 10, including postage. And that will be enough for all 4 signs, as well as my prototype, although it doesn't give me much margin for error. My orange LEDs look exactly the same, so I need to make sure I don't get them mixed up. Once again, I'm going to use that central strip from my negative, so my LED will need to be the other way up, with its notched cathode facing the middle, and the anode soldered to the bottom strip. My technique is a little bit clumsy here. For commercial application, the surface-mounted components use a solder paste which is remelted in a specialist oven, but I'm having to make do with what I've got, and even though my orange LED is a bit wonky, it'll be fine for my prototype. Now we need some wires, and for these I've raided my box of spare jumper cables. One end I can plug directly into my breadboard, the other I can strip and solder to my new lighting circuit, starting with the black for the common negative, then a standalone one for the orange LED. And for my 2 reds I've got a pair of wires, separated from a ribbon cable, so I can keep them together but still tell which is which, and not get them confused with the wire for the orange light. Each is soldered to the end of those half strips, completing our circuit which can now be connected to the controller, directly replacing my test LEDs. Plugging the wires for the anodes into where the long legs were, first for the 2 reds, and then the orange in the middle, not forgetting the black wire for the common cathode. That can go in any of the holes in the outer row. Then, with the press of the white button, our lighting sequence starts. And functionally, our scale model lights are looking good, but we've got a little way to go to get the business end looking more realistic. And clearly we need to do something with those wires, somehow getting them down through the posts of the signs. I eventually worked out the best way to do this using my prototype, but I'll spare you my experimentation, instead getting on with the build proper, applying everything I've worked out so far to get working and realistic signs, starting back on the computer where I've tidied up my design. Here I've replaced the image with graphic elements, simple rectangles and circles, which I can edit separately or copy and paste as a group. As in other videos, I won't be going into exactly how this is done in InDesign, but I am planning a guide to how to do this sort of thing using a less specialist program, so don't forget to subscribe if that would be of interest. Instead, here's the gist of how it all works. My full colour version will be printed on paper. Then I want a black and white version to be printed on acetate. These will be layered on top of each other, with another acetate layer underneath. This will have my LEDs glued behind, so I've added rectangles the size of their bodies to line them up, and made the background grey. Now I can step and repeat all 3 layers, so I've got enough for 4 signs with a couple of spares. Then I'm adding some registration targets to help line them up accurately, and while I'm here, some keep crossing clear signs to go underneath. Now to print them out, using just a regular inkjet printer, and first of all, just some regular paper. That will be the middle layer of our sandwich, and the LEDs will be bright enough to shine through it. But we want the black part of the sign to be properly opaque, which is where our transparent film comes in. Onto this I'm printing a second copy of my file, making sure I've got the matte surface the right way up, so the ink properly adheres. Then I can cut that into strips. By using exactly the same file for both the transparency and the paper, I can be absolutely sure the layers will line up, with the registration targets ensuring accurate alignment. Now all I've got to do is stick them together, and for this I'm using spray glue, which, in a really well ventilated area, I've applied an even coating to the printed side of the acetate, which can be lined up with the registration marks on the paper and pressed into place, giving us a nice shiny surface. Now we need to do the same thing with the acetate for the back of the signs, and for this I'll need to use Nature's Light Box, my kitchen window, which even on a dull rainy day provides enough light to see my registration targets on the other side of the paper, so I can line up my spray mounted acetate strip and press into place, giving me a triple layer sandwich with 3 hits of black ink, protected from scratching on the inside of the layers. Now with a brand new scalpel blade I can go on to cut the signs out, taking my time to accurately line up the edge of my steel rule, then slicing through the 3 layers, making absolutely sure nothing moves between cuts. Obviously we only need to cut out the coloured ones, the ones with the laminate. The black and white versions we can discard, but we do need to put the keep crossing clear signs to one side for later. And here's the first of our trimmed signs. All that remains is to radius the corners, which we can do with firm pressure on the scalpel blade. Now we come to fitting the LEDs. For my final design I've dispensed with the Vero board we used on the prototype. That was way too thick to be realistic. Instead, I'm working from the front to the back, sticking the face of the LEDs to the back of the sign, but the wiring will be much the same, using a common cathode for all 3 again. so reasonably confident that we know what we're doing. Let's stick them into place. For this I'm using superglue, puddled out onto a spare bit of my acetate, from where I can apply a tiniest drop to each of the four corners of my locator rectangle. Then, making absolutely sure I've got it the right way round, I can carefully position my LED, notched cathode facing the middle of the sign. Then the same with the other red light. Using superglue is quick, but you don't get long to adjust the position, so for a bit of extra wiggle room you could use an epoxy instead. Just make sure you don't mix up too much, and once again use a tiny amount. Then whichever glue you're using, apply a fine bead along the edge of the LEDs. Now onto the orange, which we've kept well away from the red ones to avoid confusion. This also needs the cathode facing the middle, where it can share a common connection with the red ones, and I need to make absolutely sure it's the right way round before sticking it down, lining up carefully with the rectangle. Then, like before, a little bit of glue along the edges, just to make sure it's secure, and then leave it for a bit to dry. For the next stage I'm going to use this stuff, Sugru moldable glue. If you haven't come across it before, you can find out more on their website. It'll also tell you where to get it. It is what it says it is, glue that you can mould, which is exactly what we want to fill the gaps between the LEDs, pulling off small amounts and squishing them in the spaces. I'm looking to build a layer exactly the same thickness as the depth of the LEDs, the size of my black rectangle, leaving the grey border around the outside, giving our sign a realistic thickness, or should I say thinness, when viewed from the side. The Sugru remains workable for quite a while, so you've got plenty of time to refine your shape, tamping the top flat, level with the back of the LEDs, and trimming the edges, squaring them up with the flat of the blade, working around all four sides using the black rectangle as a guide, and when you're happy, putting it to one side to dry. Now we need to get some wires to those LEDs, and we need a post. For this I've got some brass tube, 1/16 of an inch in diameter, that's just over 1.5 millimeters. I've also got myself some brass strip, 0.1 millimeter thick, off the end of which I'm snipping a small bit with sturdy household scissors. Both came from eBay and neither were expensive. Together they're going to form the common cathode, the brass strip connecting the negatives of all three LEDs, with the post being the wire down to ground. The wires for the three positives will go up the hole in the middle of the tube. I'll get to how that's going to work very soon, but first I need to sort out the base. For this I'm going back to my Vero board, using a small square 4 columns wide, enlarging one of the holes for the post. I want the fit to be as tight as possible, and a combination of drilling and an abrasive rotary bit means I can gradually enlarge the hole until I've got a really snug fit. I'll be soldering the end of the brass tube to that copper strip, both for the electrical connection and to firmly hold it in place. But first I want to use a bit of superglue, carefully applied around the joint so I can fix the position, ensuring the post is perpendicular to the base, in each direction, using the grid on my cutting mat. Now we can solidly fix the joint, using a bit of solder, making sure we only get it either side of the tube, and don't block the hole in the middle. Now onto the brass strip. This is going to do two things: connect the three cathodes, and then provide a place to attach the top of the post, both physically and electrically. With our Sugru flat around the LEDs, we can apply a little bit of solder to each of the cathodes, and 3 corresponding blobs on the back of our strip. Just note, don't do what I do here. The cutting mat is not a good surface to do this on. The brass strip is an extremely good conductor of heat, which is what we want when it comes to melting solder, less so when it comes to melting the cutting mat, or burning your fingers. But lessons learned, we've now got 3 good connections to the 3 LED cathodes. Now on to wiring the anodes, and for this I've got some very fine enamel coated wire, the kind of thing you get on motor windings. And the first thing to do is to remove a little bit of that insulation. And here's how I do it: flaming the end with a gas lighter, and then scraping off the burnt insulation with a scalpel, gradually turning the wire so you get all sides, revealing the nice shiny silver. Then, like the cathodes, I want to add a bit of solder onto the bottom anode, the one for the orange LED, and attach my wire. I'm doing this one first because the post will be directly in front of it and I won't be able to get to it later. I'm also a little bit concerned that it might touch, shorting between the wire and the post, so I'm covering it with a bit of insulation tape just to make sure. Now we come to attaching the post, and with the magic of editing I'm going to make this seem much easier than it actually was. I've already got a blob of solder in the middle of my brass strip, and a bit on the back of the tube, and with everything lined up with the grid and held firmly in place, all I need to do is melt the solder. Now I don't know if this was temperature, materials, solder or flux, but it took me several attempts before I got it right, and the top of the sign firmly attached, but very happy when I did. Now I can cut the wire for the orange LED approximately to length, and move on to the ones for the two reds, flaming the ends with my gas lighter, and scraping off the blackened enamelled insulation, before carefully soldering onto the pad of the LED. That's the one for the right hand, then exactly the same process for the left. A little bit of solder on the anode, and then add the wire. With all three secured to their respective LEDs, we can feed the wires down the tube, starting with the one for the amber. It's easy to lose track of which is which as they emerge from the end, so it's good to do them one at a time, making a note of the length left when they come out. The top end of the wire needs a bit of nursing to straighten out the kinks, so take your time and don't be tempted to pull it with one big tug. My wire was sold as 0.25mm diameter, but the measurement on the micrometer was more like 0.3. I guess this is including the enamel. But in any case, all three fitted quite nicely down my tube, although the last one needed a bit of wiggling to get it through. Now we come to the base, and I want to solder the other end of each of those wires to the strips on my VeriBoard, prepping each exactly as before. I know which is which from the length of the protruding wire, and I'm starting with the red light on the left, soldering the wire to the strip on the corresponding side of the board, then the wire for the orange in the middle. The one next to that is the common negative, already wired through the post, and finally the wire for the right-hand LED, all logically laid out in the same order as the lights at the top. Now one thing we didn't need to worry about was the post shorting out with the orange LED. Our gap is plenty wide enough, so we can dispense with that bit of insulation tape. Then with some masking tape over the face of the sign, I can give it a quick spray with grey paint. Now one thing I'm not completely happy with is the colour of the lights in their off position. The colour of the LED does all the hard work when they're on, so I just want to make them a bit darker, using a suitable black pen and a cotton bud to even them out. I'll adjust my print file accordingly for the other three signs. To finish up, I just need to add the light hoods, and for these I'm repurposing a bit of heat shrink, the stuff more commonly used to insulate joins in wires. Unlike regular plastic tube, the advantage is the wall is very thin, which will be much more realistic. It's also much easier to cut, particularly at an angle which we need for the shape. Just flattening out the tube while we make the incision. It'll spring back to its roundness afterwards, when we can put it over the light. Now we come to what's possibly the fiddliest part of the whole operation, sticking them down, and I'm using superglue again, carefully dipping the end of each piece of heat shrink into a puddle of glue I've got on a spare piece of acetate, before very carefully manoeuvring them onto the sign, the surface of which we want to keep as clean as possible from excess glue. So any bits I've missed or aren't sticking properly need only the tiniest amount of glue applied with a cocktail stick, and then pressed home with some tweezers. With all the internal wiring for the signs complete, we can set about mounting them on the level crossing itself and wiring them to the controller, starting with the base of the signs. I'll be using some fine decoder wire, the stuff I use when chipping a loco. Unfortunately, I've got all the colours I need, black, orange and red. This is much easier to work with than the enamelled wire, especially with some precision wire strippers, and soldering much more straightforward. Effectively, these are really just extensions to the internal wiring, but now colour-coded, so each solders to the same strip as the one for each LED, with a black one on the strip for the post, providing the common cathode for all three. These are going to go through my baseboard and eventually connect to the controller, so I'm snipping off a generous length before soldering the last red wire, the one for the left-hand red LED. When all four wires come out the other side of the board, I'll obviously have two reds, so I'm leaving that last one a little bit longer, so I can tell them apart. Then threading all four through a piece of heat shrink tubing, I can keep them together, ready for mounting. For this, I'm going to need to do some excavation, and I've marked out the position of the sign base on my level crossing, close to the gate post. Then for the wires, I need to drill all the way through my layout board, the plastic level crossing, 2 layers of foam board, and then the MDF underneath. Now I need a rectangle for my sign base, just cut through the top layers. The foam board will be easy to work, the plastic of the level crossing a little less so, particularly on my slightly spongy surface. But a combination of drilled holes and a sharp knife soon gets me a rough rectangle, which, checking for size against the base, I can gradually enlarge, tidying the edges as I go until I've got a neat fit. Then it's a case of threading the wires through the board, and out the other side, finishing with the heat shrink collar, setting our base in the rectangular cutout, where it fits snugly. Now, if my layout was a permanent setup, I'd glue it firmly in place, but as a precaution against any minor knocks, damaging the signs themselves when moving the board, I'm using a bit of white tack just for a bit of give. Now to make 3 more signs, and I've adjusted the print so that the circles are a bit duller, to be more realistic when the lights are off. Otherwise they're exactly the same as the first one, and fit on the baseboard in exactly the same way, with the wires threading through the hole. Once again, I've left the one for the left-hand red LED a little longer, so we'll know which is which when we wire to the controller, which we come to now. On the underside of my baseboard I've cut a recess in the MDF, and into this I'm going to glue a bit of Veriboard with 4 strips for my 4 connections, and these I'm going to label with my label maker, using the same letters as in my code. But as this is going to be upside down, I'm going to do it back to front, with RR on the left and RL on the right, and it's with the wire for RL that we're going to start. That's the one that's longer than the other 3. But now we want to trim it to a convenient length to reach our board. Strip off the insulation and solder in place, just at the end of the appropriate strip. Eventually each strip will have all 4 wires from each of the 4 signs, but for now I'm just doing the front 2, and that's the right hand LED of the right hand sign that's going on now, followed by the wire for the orange, and then the black for the common negative. And then exactly the same thing for the left hand sign, starting with the wire for RL, the one that's slightly longer, then the other red, the orange and the black exactly as before. With the signs connected together, we now need to connect to the controller, and for this I've got a convenient bit of ribbon cable, with plugs at one end and sockets on the other. We won't need the sockets so they can be snipped off and the wires stripped, ready to be soldered to our board. Clearly the colours don't match exactly, but it's pretty easy to work out what's going on, and when we're done we can flip the board over again and plug into the controller. First the 3 anodes, which go exactly where they were before, then the common cathode, which can plug in next door to the nearest ground pin on the Pico. As soon as we power that up, the code starts running, and a push of the white button will instigate our lighting sequence. First the orange on its own, then the 2 reds, and then the wigwag. And everything's working perfectly, and my signs are looking great. Turns out my 402 ohm resistors were about right after all. Now for some finishing touches. On the base of my sign I've moulded the mounting plate out of Sugru, and now it needs a coat of paint, carefully covering the sign and using a rough torn mask around the base. I'm also using some Stone Effect texture paint, just to blend it in. And finally a bit of gravel, just sprinkled on the wet paint, and brushed away when dry. Now for some finishing touches to the code, and I've popped out to my local level crossing just to check the timings. I've also noticed for the first time that the 2 red lights go out before the wigwag starts, so I want to factor that in as well. And with the Pico plugged back into the host computer, I can access the program, opening it through Thonny and making the changes I need. First of all, adding that bit where both red lights go out, simply copying and pasting those 4 lines and changing the values to 0. And this is what my finished code looks like. The orange light comes on for 4 seconds, both red lights together for 0.4 seconds, off momentarily, and then the wigwag of 0.4 seconds each. All derived with a bit of trial and error, visually comparing my model signs to the video of the real thing. But above all, it feels right, and happy with the outcome, I can save, close the program, and exit Thonny. Now I can retrieve the printouts of my Keep Crossing Clear signs. I've laminated the paper and the acetate, in the same way as before for a bit of rigidity and a nice glossy surface, and when they're trimmed I can stick them onto the posts, again using superglue and a little bit of patience to get the position right. I'll also need to clear up some of that overspray that's gone onto the post. Now the look of my crossing signs is very much of the modern era, so great for a contemporary layout. The red and white borders were introduced in 1992, but what if you're modelling something a little earlier? And here's a bonus for any rail blue fans, a white printed border, which can be incorporated right from the start, or even added as a frame later. Printed on glossy paper and cut out, temporarily stuck in place with some repositionable spray mount. Then you get the best of both worlds. That'll get you right back to 1968, when the orange light was introduced. And that completes our realistic level crossing sign project. If you want to give it a go yourself, I've put a list of the components in the description, along with some prices. I reckon I didn't spend more than £25, a lot less than the off-the-shelf alternatives. And I've still got the option for expanding the features, approaching train detection, and even those servo-controlled gates. But really you need a bigger layout for those. I suspect the guy in the transit van is going to wait a long time for the gates to open.